when we run a chemical reaction and you form it out, you write this thing called an equation. You know, this is one of the greatest threats to human beings. Oh no, not a chemical equation. And then you say, oh, do I have to balance it? Oh, I can't. How can I balance it? It's so simple, and I just wanted to go through some with you and show you how easy it is and that it makes perfectly good sense. I want to show you a chemical reaction that's extremely famous, and we'll put it down and then talk about the qualities of it. Here it is. If I take hydrogen gas and I combine it with oxygen gas and I apply a spark, for instance, I will get an explosion. And the explosion will yield something very interesting called water, H2O. Now that, ladies and gentlemen, is a fact. Why do we know that? Because we have a laboratory. We go to the lab and we can try it. You will see this demonstrated at some point. But first, I have to tell you that this is a chemical equation. So an equation has to be, it must be a fact. It's got to be the truth. And that is true. Okay, now when you write the equation, you have to have knowledge of chemical formulas. I have to know that hydrogen is a molecule, H2, oxygen is a molecule, O2, and water is a molecule, H2O. I have to know the background of how to write formulas. So, the equation is a fact, and you must have correct formulas in that equation. So if you come in and write an equation with the wrong formulas, you're going to be in very big trouble. Then it won't be a fact, and when you try to balance it, you'll have trouble. Oh, balancing. This is a nightmare to some people, but it's fairly simple. It's logical. Have you ever heard from about the 6th grade, matter can neither be created nor destroyed. It's just moved around. Have you heard that mass cannot be created nor destroyed? It's moved around. And we're going to find out that energy is the same thing. You can't make energy. You just move it around. So, in this equation, I have got to obey the law of conservation of matter, which includes atoms, molecules, and I have to conserve mass. So I must balance equation. And that really means you're going to obey the law of conservation of matter. Can we leave it there? I don't know if you can see this arrow here. But the mass on this side, the mass on that side has to be the same. Therefore, the atoms on this side and the atoms on that side have to be identical in count. And that's all you do in balancing. For instance, it's simple. I've got 2 hydrogen atoms here in this molecule. Oh, that's great. I've got 2 hydrogen atoms in the water. I'm really happy. Okay. Oh, I've got 2 oxygen atoms here, but only 1 over there. What do? Hey, you're not allowed to change the formulas. That's one of our little rules. You have to keep the formulas that are correct. All I can do is I can say, well, maybe I make 2 water molecules. I'm allowed to put a number in front. So now it's reading, 2 times water or 2 water molecules. It's that simple. Okay, so now I'm happy again because I got 2 oxygens here and 2 over there. But I quickly realized with my human brain that I now have 2 times 2, or I have 4 hydrogen atoms, and only 2 over there. So what am I going to do? That's right. I'm going to put a 2 here. And now, here's what we've got. If I do the atom count, 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. But now we use a slightly different approach in dealing with this. You remember that a mole of a substance is 6.022 times 10 to the 23rd particles. It's also equal to what is called the mass weight in grams. It's, you know, we can calculate the weights, we'll do that. But what I want to say is that an application of the mole is that when you put these numbers in front of here, you're telling the number of moles. And here's how this reads. It says that 2 moles plus 1 mole yields 2 moles. Or 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. People say, that doesn't add up. But if you go back and count atoms and do the masses of the atoms, it adds up. Moles don't have to add up on one side of the arrow to the other. So balancing the equation is essentially balancing the masses, in my opinion. That's just me. Well, everybody else seems to think that too. Let me elaborate a tiny bit more. So this is how I read it. It's balanced, and if I count atoms, everything works lovely. You might remember from the periodic table that hydrogen has an atomic mass unit, or you know, its molar mass for hydrogen is 1.00. I'm going to just use 3 significant figures, and I'm rounding, so don't get too excited. And oxygen is 16.0. Well, what that means that every time you have a hydrogen atom, you've got 1 unit of mass. And here I've got H2, so it would be 2.00. Plus 2 times 16, you can do that, 32.0 yields 18.0. That'd be a water, there's an oxygen, and there's an H2. But you see this red 2 in front? I got to multiply that by 2. Oh, by the way, there's a 1 here. Just assumed to be there. And over here, I've got to multiply this by 2. Because I've got 2 moles times the molar mass of 2. And 1 mole times 32 and 2 times 18. If I calc this out, simply put, this equals 4.00 plus 32.0 yields 36.0. And again, please excuse my figures and so forth. The concept is here. This is the conservation of mass, conservation of matter. And if you add this up right here, you're going to get 36.0 yields 36.0. Same number of grams have to be on both sides. If you want to test an equation, if it's balanced, it's a long way to test it. But this is going to be true. I'm allowed, if I want to, I can put G's here, which are grams. And in that case, I can say that if I start with 36 grams on this side, I get 36 on the other. Now, just a couple of little things about this equation. Have you ever heard of the space shuttle? The rocket engines that send the things into outer space, the rockets. You've probably heard of them having some problems with leaks in the liquid hydrogen or the liquid oxygen. The rocket engines run on this equation. This is, I like to call it the space shuttle reaction, because they liquefy the gases, fill the tanks, and they literally spark it, and they get a tremendous amount of energy. I didn't mention the energy, but actually this reaction gives a lot of energy, as you'll see in the demonstrations. Very energetic. Oh, just keep this in mind. When we study energy in more detail, energy is also conserved. So whatever energy is given off during this reaction, going from left to right, if I reverse the reaction, I have to put in the same amount of energy. Water is a tough stuff. It's very difficult to get water to come apart. So chemical equations can typically be thought of as there's a very high likelihood they can run in both directions. And on both sides of this arrow, this is very important. Arrows are very important. Energy and mass are conserved.